Today I'm bringing you another module that I put together that actually simulates some types of switches, and this is it right here. But before I power this up and let you guys see exactly what it does, I want to show you the diagram for it because it would be easier to understand what you're looking at on paper here. So this is the actual circuit, as you can see. I've got two buttons right here, just push buttons, momentary push buttons, and a bunch of LEDs and transistors and one IC. That IC is a 7404, okay, just a standard TTL hex inverter. So, and the rest are all resistors and whatever. But I'm going to put this aside for now, get to the diagram, and explain what I've done here. Then I'll show you this in operation. All right, so I'm just going to put this aside for the time being. And I want to show you guys here the diagram. This diagram is for this circuit, and basically this is how simple it is. It's got the 6 gates here, but these 6 gates in that chip is only in one package, so it's only one IC here. And these are the transistors and the resistors and so on. So what you're looking at is you're looking at a couple of types of push button systems, and this one down here is actually a simulated double pole, double throw switch, but it is an electronic version of it. So I'll begin at the top one here. This one here is considered a alternate action push button, because here's the button right here. When you push that, every time you push that button, the output here changes states, but that state is held. So you basically just push the button, let go, and then whatever state the output is at, it stays at that state. It doesn't go back to normal. All right. And the reason it does that is because you have a feedback resistor here. The way this one works is that obviously signals at the inverters are inverted at the output. Whatever the input is opposite. So when you push that button there, if you assume that this capacitor is got no charge on it, that would be low level or 0. So by pushing that button, you're applying a 0 level or low level into the input. The output goes high, so that high signal there starts to recharge the capacitor through the resistor. But the switch is no longer down, okay? You have already let go of that switch. So this high signal is just recharging the capacitor. It's getting ready for the next pulse. The low that you were initially applied here by pushing that switch is obviously changed to high and then low again. So that low condition at the output here gets fed back through the resistor, the feedback resistor, into the input, and it maintains that state. All right, so the whatever level the input is here, the output level is the same, and that state is held by the feedback resistor. And then I'm using a third gate here because I just basically use that as a buffer to eliminate any loading of the circuit due to low impedance on the outside. So every time you push that switch, the output changes states, and then it maintains that state, and that's it. All right, so this is called alternate action push button. This system right here, this is basically the same wiring as these gates, except you only have one capacitor here. This capacitor has two functions. Number one, electrostatically, it maintains a high level on the input here, especially when the switch is not pushed. When you don't push this switch, this side of the capacitor, this side of the switch, and this input of the gate, they're all floating. It's not tied to VCC, and it's not grounding through a resistor, so it is in a floating state. A floating state basically indicates it's a high state. The output here will also go high because it gets inverted and then inverted again. So this is similar to this circuit. Whatever the input is, the output is. Now in this case, because you have the output is somewhat forced to go high, that high electrostatically goes through the capacitor which maintains this input high as well. Not directly electrically, but electrostatically, it maintains a high level. The only way that this circuit here will change states is by pushing that button. So if you don't push this button, the output here will always be a low, because this output will be a high all the time. And obviously it gets inverted, so this is always off. It's always in a low state. But as soon as you push that button, the output will go high, and it stays high only if you hold this button down. If you don't hold this button down, it'll go back to normal, to the low state. Okay, so this is a momentary push button system that changes state only when you push the button and hold it. This one here will change states alternately. Every time you push the button, it'll go high, and then push again, it'll go low, and so on. And that's basically the two different systems for push buttons. Now down here, what you have is you have a simulated version of a double pole, double throw switch, and I might think I probably have one here somewhere. Just give me 1 sec here. Let me take a look. Yeah. Okay. I've got one right here. Got one right here. Double pole, double throw switch. You guys have seen this. Obviously, it's so common. You know, they are just everywhere. So basically, you have this one here has a center off position. This circuit does not have a center off position, but this switch, if it didn't have a center off position, it would only have two positions. It would have either this position or this position, and in both positions, it will connect the center pins to either the top side or the bottom side. That's what this circuit does, okay? But instead of mechanically moving the switches in this case, it does this electronically. The way it does it is by sending a signal into the two transistors in a vertical direction, but it's controlled horizontally. So as you can see here, it's wired. The way I've wired it is the two collectors are connected together, top and bottom, and these collectors serve as the common pins for both top side and bottom side, but independent of each other. Now, to control the connection point between the center pin, which would be the collector, and this pin, you have to turn this transistor on. When you turn this transistor on right here, it's basically like putting a short circuit right across these 2 points, collector emitter. And that simulates the closing of a switch, of a contact, okay? So you do this to the top side and you do this to the bottom side. So that's why you need to turn on these transistors top and bottom, because you want to connect these 2 points and these 2 points. It's similar to taking a switch like this, where you have the contacts the way you see them on paper in this direction, and then you flip the switch over. So what you're doing is you're connecting the center pins to these 2 pins, and that's what this is doing right here. So now, and that happens when the output of the push button up here is switched so that the output at this gate is high, because the input of this gate will be low. Now the low coming from here, this point, will keep these transistors off, but it will turn these transistors on. So the switchings will be between the center points and the right side. All right, so it's basically like having these pins shorted across this way. And then when you hit that button again, the top button, the states will change, and then it will connect from the collectors to the left side, because now these transistors will be off and these will be on. So it's like taking the switch, here and just flipping it from this side to this side, okay? Or let me show you this way. This side, it's just back and forth switching like this, where you're connecting one side to the other side. So, but instead of using a mechanical switch, I'm doing it electronically, and I'm doing it with this system here that only requires one push button. And that's exactly what this circuit is right here. All right. So that's as far as the explanation goes, diagram-wise. So let me put this aside, and we'll basically, I'm going to show you what I just talked about from the diagram. So I'm just going to bring in some power here, and we'll connect this. Now you'll see here that I have these wires. I'm not sure if you can tell, but I've got these wires here disconnected because these are the drivers for the transistors. And I just have it disconnected for the sole purpose of demonstration. But what I'm going to do is I have these resistors right here. I'm going to reconnect these to the base and the base drivers here. So this one for that side and this one for this side. Because these ones here can stay in place. They don't really activate while the system is off. But I'm going to leave the two wires here. I'm going to leave these disconnected because if I connect these, then both these circuits, the momentary push button and the alternate action push button, will interfere with each other, and you don't want that. So I'm going to connect these wires one at a time. So anyways, here we go. I'm going to plug this in, and we're either going to get something or not get something. Okay, and we get nothing. All right. Now, first thing is I'm going to show you the momentary push button, which is on the top part of the circuit here. So I'm going to connect this wire here. Now, as soon as I connect this wire, what will happen is the, excuse me, that's my light. I'm having some trouble with this light still. Now, what will happen is these two LEDs on this side should come on because that is the normal output, state output on power up of this circuit. So here we go. I'm going to connect this, and hopefully all right, there we go. Okay, now it's showing that these two lights here are on. So what that basically is telling you is that the connection of the switch is between the center part here, where the resistors are simulating the center pin of the switch, and so it's connecting from common. These are your common points where the resistors are, and it's connecting from common to the right side of the switch. So these LEDs are basically telling you that the right side of the switch are connected right now. Okay. Now, if I push the switch down, it's only a momentary system. So in other words, you have to hold the switch down in order to keep that position. Okay, so if I push it down, you'll see the lights will switch to the left side. There you go. All right, but you have to hold this position down in order to maintain that state. Oh, excuse me. Okay, let me take these LEDs off here because these are indicators for the actual IC output. We don't need that right now. All right, so by holding the switch down again, okay, it switches to the left side. So that's basically the same thing as taking a mechanical switch, such as this, and flipping it from one side to the other side, like this, okay? But not keeping it in that side, only keeping it on the left side momentarily. And as soon as you let go of the signal, it automatically reverts back to the normal side. So that's what this simulates right here, okay, by a momentary push button. Because you can see as I'm pushing it down, if I don't push it down, this is the normal state right there. And if I do push it down, it'll switch positions, but I must hold it. Okay, so that's the function of the momentary circuit. Now, if I disconnect this and connect the alternate action one, the alternate action also has this as a normal state, the right side. Okay, the difference is that when I push this switch now, this is for the alternate action circuit. As soon as I push this, I just need to push it one time and the outputs will change. I think I pushed it already. and it's gone to the left. But you see, I'm no longer touching the switch, and it holds that position. If I hit it again, it'll go back to the right side, okay, like that. And it holds that state. Push it again, it holds the left state. Push it again, holds the right, left, right, left. And that happens at every push of the switch, but it maintains that status. Now, what this part of the circuit does is it takes the switch and basically switches it from one position to do something in a circuit, and then flip it to the other position to do something else, all right? So you have two different versions on the circuit. Now, what you're looking at here is not exactly how you would build it. I only used the LEDs to show you the function of this circuit. The LEDs are just indicating position levels, but you wouldn't actually build it like this. The way you would actually build this is by not using the LEDs and not using the resistors, only using the transistors. And I'll give you an example of that. Let me get another piece of paper, and I'm just gonna draw something down for you, and I'll show you what I'm talking about. So I'll bring this in here. All right, so if we have, for example, let's say, for example, you have a circuit that needs, there's power, and then you have a resistor, and that has to go to a capacitor to ground. But before you do that, you want to switch it. So let's say that you have a switch right here, okay, and then it goes to a capacitor to ground. Now, so in order to close this circuit, you have to put a switch right here. And you have to mechanically close this switch, and it will connect the resistor to the capacitor. But suppose you don't want to use a switch, okay? So what you do is you use this circuit right here with this function, one position, the other position, or you could use the top function. It really doesn't matter. But instead of using a mechanical switch, the whole idea is that you would use this push button circuit, which is just an electronic version of a switch, and you take the output of that into a resistor right here to any one of these transistors, or all of the transistors, whatever you need. And instead of connecting your transistor in a normal fashion, such as a load going into the collector and then the emitter is grounded, what you would do is you would take the collector of that and connect it to the top part here. So the signal from this source comes through into the collector. Then the emitter, instead of going to ground, would go to this point right here. So basically the transistor is acting as your switch, which is controlled by the push button. All right, so this is just one example of how you would use a system like this. And for me, it's much better because what it does is it eliminates the actual mechanical version of a switch that can give you a lot of problems. And when you put this in a project box, you also have the advantage of not having this part of the switch stick out of the box. Because if you use these buttons, these type buttons, you can basically build it in a box where it's flush with the front panel, and it looks better, and everything looks uniform. And it's basically just by pushing buttons to give you your selection. You could still use mechanical switches. I mean, nothing wrong with that, but I prefer doing it like this. And this is the diagram, the other diagram that I showed you here. This is actually how simple it is to make it, okay? So, and again, these are parts which are commonly found everywhere. I mean, this is a 7404. It's a TTL standard hex inverter chip. And to build a debounced push button can be as simple as this. This one here only has 3 or 4 parts, and this one here actually has only 2 parts. It has the switch itself, and it has a capacitor. And in both cases, actually, these are debounced because the capacitor in this circuit has two functions. Electrostatically, it couples the high output back to the input to keep the initial status without energizing the switch. And the other function it has is it acts like a snubber. And what it does is it snubs out any transients or switch bounces from the switch. It absorbs it. And and that's all you need to make this work. This one here, now, I wanted to mention also, if it does not work, you can try and change the value of the capacitors. I usually use about 10 microfarad. You can use 100 as well, but it'll take a little bit longer to switch between intervals. So 10 microfarad seems to work fine. If it still doesn't work, you may try to try a different type of 7404, or you can add a 100,000 ohm resistor from the input side here to B+, and that will make it work better. Now, on this circuit here, this is also debounced because the actual capacitor will absorb some of the transients from the contacts in here. But even if this is bouncing, during the time that this is bouncing, when you press it, the capacitor itself is either charging or discharging, so it doesn't have enough time to change states. And as soon as it makes initial contact, the output from the one gate will immediately feed that signal back to the input, and it maintains that state. So the resistor itself in this circuit is actually the component that eliminates a switch bounce, more so than the capacitor does. So in both cases, they're both debounced, and this is how you would build a mechanical switch, an electronic version of mechanical switch to simulate the same as a mechanical switch. In my case, I built a double pole, double throw switch, but you can make anything you want by adding more transistors, more lines, more resistors. You can make anything, a 4-pole double throw switch, single pole, single throw, single pole, double throw, any kind of combination of switches, you can make it like this, okay, that you would need. So that's it, guys. There you go. Simplicity in the works here, and the circuit itself right here, which works very well, okay? I hope you guys enjoyed this video as well, and I hope you also find it helpful in any kind of designs that you guys are doing for yourselves. You can certainly incorporate this kind of system here for any kind of switching that you need, and I hope you find it useful. So with that, I'll just say have a good day. And we'll catch you on the next video. I hope you guys enjoyed this one. Do not forget to subscribe. I love bringing this to you, these kind of things. And I do enjoy it. And I also appreciate very much that you guys subscribe to me and, show me that you're supportive of what I do. And I am really, really appreciative of that. And I just wanted to say thank you to everybody who has done so far. And I hope that keeps coming. So, and that basically gives me more incentive to continue on with these kind of little circuits that I'm more than happy to just put it out there and let you guys, do whatever you need to do with it. Okay. So with that, guys, I'll say have a great day. Until the next video, we'll catch you next time. Thank you so much. Take care. We'll see you later.